Hello everyone, this is the second video in our 6-part training series based on the FR5969 launchpad from MSP430. This section presents an overview of FR5969 core architecture and peripherals. 430's proprietary low-power architecture core supports the MSP430X CPU that incorporates features specifically designed for modern programming techniques such as calculated branching, table processing, and the use of high-level languages such as C. The X in the MSP430X CPU stands for Extended Addressing Modes, and the CPU can address up to a 1 megabyte address range without paging. The MSP430X RISC CPU includes other features such as an orthogonal architecture, full register access including program counter, status register, and stack pointer, single cycle register operations, large register file that reduces fetches to memory, a 20-bit address bus that allows direct access and branching throughout the entire memory range without paging, a 16-bit data bus that allows direct manipulation of word-wide arguments, a constant generator that provides the 6 most often used immediate values and reduces code size, direct memory-to-memory transfers without intermediate register holding, and byte, word, and 20-bit addressing. This slide illustrates all of the sources of system reset, including a brownout reset or BOR, a power on reset or POR, and a power up clear or PUC. Different events trigger these reset signals and different initial conditions exist depending on which source triggered the reset. Similar to the F5XX flash family, the FR59X features 7 operating modes for standby operation ranging from LPM0 to LPM4.5. These modes are selected based on the need for clock frequency, power requirements, and the type of peripheral that needs to be enabled while in standby. This slide shows the various system power consumption numbers when the device is in modes LPM0, LPM3, LPM4, LPM3.5, and LPM4.5. Selecting the right mode for your application is easy. LPM0 is an ideal choice for applications using a high-frequency timer to trigger an interrupt, allowing the CPU to be turned off while still providing for a fast wake-up. LPM3 is the preferred mode for low-frequency peripherals. It allows the operation of the RTC crystal while consuming less than 700 nanoamps. In LPM4, all the system clocks are turned off and a device wake-up is possible only from an external interrupt such as a switch triggering a port pin. LPM3.5 and LPM4.5 are more specialized modes that allow the digital core to be turned off while retaining minimal functionality, allowing the device to hibernate. LPM3.5 is the lowest standby power mode in which the device can maintain a real-time clock, wake up on clock or alarm events, or from a switch interrupt. The wake-up time from this mode is longer than typical low-power modes because the core regulator that was switched off on entry needs to be powered back on. LPM4.5 is also known as deep shelf mode. An example application where this mode is used is to store battery-powered products that are stored in warehouses before shipping to an end user. These products are required to consume extremely low power while maintaining the ability to wake up from a switch interrupt. Both LPM3.5 and LPM4.5 are ideal for applications that have low active duty cycle and slow response time events. In such applications, maximizing time in LPM3 or 4.5 can reduce power consumption greatly. This slide provides a quick overview comparison of wake-up times for various low-power modes across different 430 families. Applications require different active duty cycles depending on the functions they are executing. In cases where the active duty cycle is high or the device needs to respond to events on a highly frequent basis, a shorter wake-up time is preferred. As an example, the CPU may be turned off and the device placed in LPM 0 while waiting for a high-frequency UART data byte to be received. In general, low-power modes 0 through 4 exhibit faster wake-up because the digital core is kept powered. Wake-up time from LPM 3 or 4.5, on the other hand, is similar to waking up from a power-on reset. In this slide, you can see the comparison between different families of the 430 starting from the F2XX all the way to the FR59X. For more accurate information on wake-up times, please refer to the device datasheet. The Power Management Module, or PMM, manages all functions related to the power supply and its supervision for the device. Its primary functions are first to generate a supply voltage for the core logic, and second to provide a mechanism for the supervision of both the voltage applied to the device at the DVCC pin and the internal voltage generated for the core. The PMM uses an integrated low dropout voltage regulator to supply the core voltage while being powered from DVCC. The core voltage supplies the CPU, memories, both flash and RAM, digital modules, while the DVCC supplies the IOs and all analog modules, including the oscillators. The FR59XX has an internal core voltage, and the device can be operated at the highest clock frequency of 16 MHz down to the supply rail of 1.8 volts. Hence, the frequency of operation is independent of the supply rail. The power management system on the FR59 plays a significant role in lowering the overall system power. The PMM uses an intelligent mechanism of power gating, which in combination with the predictive LDO ensures that the system is constantly and dynamically adjusting to changing load requirements in a manner that is completely transparent to the end application. Since the core LDO is buffered by internal capacitors, there is no need for external buffering as in the F5XX family. This not only reduces peak and average power when charging the capacitors, but also brings down the total system cost. The main function of the supply voltage supervisor is to oversee DVCC. By default, the SVS is turned on for all power modes. It is possible to disable the SVS to save power in some modes such as LPM3, LPM4, LPM3.5, and LPM4.5. As mentioned in the previous slide, the PMM provides a means for DVCC and the internal core voltage to be supervised. When the device is powering up, the SVS ensures that a power supply is stable and available before releasing the device from reset. The SVS is on by default at power-up, ensuring that the device only starts to execute code when a clean supply rail is present. After powering up and during operation, the SVS function detects when the supply voltage falls below a specified threshold and alerts the application accordingly. In the FR59X device, there is an additional option to set the device in LPM 4.5 when an SVS event due to power fail occurs. In this case, the device fires a system non-maskable interrupt instead of issuing a reset. This allows the application to safely turn off critical tasks, block IOs, and disable the SVS to further save power before entering LPM 4.5, ensuring optimized usage of the remaining battery power. This slide presents an overview of the FR59XX family clock system. The main advantage of the orthogonal FR59XX clock system is its ability to branch any clock source to any system clock. There are 2 external and 3 internal clock sources. The external clock sources are low-frequency oscillator, typically 32768 Hz for the RTC, high-frequency oscillator with a frequency limit between 4 and 24 MHz. The internal clock sources include the VLO, a very low power, low frequency internal oscillator that operates at approximately 10 kHz, the DCO, a high frequency digitally controlled oscillator with factory calibrated frequencies, and the MODOS, a 5 MHz oscillator used internally for peripherals such as the ADC. These clocks can be used to source the CPU clock, also known as main clock or M clock, the high-speed peripheral clock, also known as sub-main clock or SM clock, and the auxiliary clock or A clock. The default startup frequency for the system is 1 MHz sourced by the DCO. The table shown on this slide provides a listing of the different programmable calibrated DCO frequency settings. More details on these settings and their tolerance can be found on the device datasheet. The FRAM controller is the interface between the FRAM array and the CPU. Its function includes controlling the access speeds to FRAM to ensure that it does not exceed 8 MHz independent of the system frequency. FRAM read and writes are similar to SRAM and need no special handling. The FRAM controller contains a cache with 2 cache sets. Each of these sets contain lines which are preloaded with 4 words during one access cycle. An intelligent logic selects one of the cache lines to preload FRAM data and preserves recently accessed data in the other set. If one of the 4 words stored in the cache lines is requested, also known as a cache hit, the FRAM is not accessed and the word is retrieved from the cache. However, if none of the words available in the cache are requested, also known as a cache miss, then the required instruction or data is fetched from FRAM. Access to the cache is completely transparent to the user, and the usage of the cache is always enabled. In a typical application, the cache hit ratio is between 66 to 75%. When the system frequency is set to higher than 8 MHz, wait states to access FRAM need to be configured in application using the FRAM control register. The FRAM module also has built-in ECC logic that is capable of detecting and correcting bit errors. There are 3 options for programming an MSP430 FRAM device. 1 is programming via Jtag or the SPI-by-wire interface. 2 is programming via the ROM BSL, and 3 is in-system programming. In the next section, we will discuss methods to secure the device when using these methods to program the 430. Once an FR59X device is programmed, the following options can be used to secure it from external access. Programming the Jtag fuse by disabling Jtag or locking it with a password, disabling the bootstrap loader to prevent unsecured access, and protecting a portion of the code such as sensitive IP by using the IP encapsulation feature. Each of these are discussed in more detail in the upcoming slide. Programming the Jtag fuse is achieved by writing to the Jtag signature located at addresses FF80 and FF82. The content of these locations varies depending on whether the user would like to secure the device such that only BSL access is possible, or secure the device with a unique password that can then be supplied via the toolchain to open the device. The pros and cons of these 2 options are discussed in the next slide. As mentioned in the previous slide, users may select any one method of securing Jtag access depending on their application. In cases where security is a primary concern, it is preferable to lock the Jtag without a password. Once this is accomplished, the device can only be accessed via the BSL. This involves knowing the BSL password, which is longer in length, making it inherently more secure. In this case, however, the user must make the 2 BSL lines available externally if the ability to update firmware is required. The second option, securing Jtag with a password, involves generating a unique password that is stored in the IDE such as CCS or IAR. When the device is accessed from an authorized source that is able to provide the correct password, Jtag access is made available once again. IP encapsulation. Manufacturing trends have changed greatly in the past decade. It is now not uncommon to program a device in different stages of end equipment manufacturing involving different third parties and geographic regions. In some cases, it is desirable to protect a certain code segment from external access via Jtag or BSL while still allowing a third party to program the device. An example of such an application can be in a metering device, where the billing algorithm is protected while allowing different subcontractors to program their own user interface code. In such cases, the IP owner can protect their IP by using the IP encapsulation feature in the FR5969 device. This feature allows the creation of a special address range in main memory with no external access whatsoever. Only execution of code from the protected segment is possible via an external function call. Any external access via Jtag, BSL, DMA, or even an in-system register read is prevented. An unauthorized access to an IP encapsulated segment returns a value equivalent to jump dollar and triggers an interrupt or reset. The Aes Accelerator module performs encryption and decryption of 128-bit data with 128, 192, or 256-bit keys according to the Advanced Encryption Standard. Some key features of this module include the ability to perform 256-bit encryption and decryption in 234 cycles. In comparison, a software algorithm takes a few thousand cycles to accomplish the same. The module also allows DMA usage for autonomous operation and provides an AES-ready interrupt flag once encrypted data is available. The Aes Accelerator module provides automatic clock activation for mClock for use with low-power modes. When the Aes Accelerator is busy, it automatically activates mClock regardless of the control bit settings of the clock source. The clock remains active until the Aes Accelerator completes its operation. The FR5969 device also provides a random number stored as a seed for a deterministic random number generator. This unique seed is programmed at test and is generated by an offline test programmer using a cryptographic random number generator. This is useful for creating unique serial IDs and also for key generation. The digital I/O module includes individually programmable I/Os. It also contains interrupts on ports P1 through P4 and configurable pull-up and pull-down registers, among other features. Typically, pin functions are multiplexed, and the selection of a function other than GPIO is performed by setting a combination of the DIR and cell bits. The device datasheet covers the various portions of each pin function and the corresponding register setting. The Capacitive Touch Io module allows implementation of a single capacitive touch sense application. The module uses the integrated pull-up and pull-down resistors and an external capacitor to form an oscillator by feeding back the inverted input voltage sensed by the input Smith triggers to the pull-up and pull-down control. Any GPIO can be switched to capacitive touch state by enabling a bit in the control register. The resultant oscillating signal from the Capacitive Touch Io is measured via an internally connected timer. Analyzing the timer values allows the end application to determine if a touch has occurred. The Capacitive Touch Io module allows the application to be low power with its autonomous operation and also results in lowered system cost due to reduced external components. The Enhanced Universal Serial Communication module supports multiple serial communication modes with one hardware module. The EUSKI-A module supports UART and SPI communication, and the EUSKI-B module supports SPI and I2C communication. When used in UART mode, some features of the EUSKI-A include configurable 7 or 8-bit data with odd, even, or NOR parity, independent transmit and receive shift registers that can be read from or written to using DMA, built-in idle line and address bit communication protocols for multiprocessor systems, receiver start edge detection for auto wake up from LPM modes, programmable baud rate with modulation for fractional baud rate support, and independent interrupt capability for receive, transmit, start bit received, and transmit complete events. In terms of SPI, the eUSKI A and B are both capable of SPI communication in both 3 and 4-wire modes. In SPI mode, serial data is transmitted and received by multiple devices using a shared clock provided by the master. An additional pin controlled by the master, UCSTE, is provided to enable a device to receive and transmit data. Some features of the SPI module include 7-bit or 8-bit data length, LSB first or MSB first data transmit and receive, independent transmit and receive shift registers, selectable clock polarity and phase control, and slave operation in LPM4. I2C mode is only supported by the eUSKI-B module. In I2C mode, the eUSKI-B module provides an interface between the device and I2C compatible devices connected by the 2-wire I2C serial bus. External components attached to the I2C bus serially transmit or receive serial data to and from the eUSKI-B module through the 2-wire I2C interface. The eUSKI I2C module features many enhancements when compared to modules of previous generations. Some of these enhancements include 7 and 10-bit addressing modes, multi-master transmitter and receiver modes, up to 4 hardware slave addresses with independent interrupts and DMA triggers, clock low timeout interrupt to avoid bus stalls, 8-bit byte counter with interrupt capability and automatic stop assertion, mask register for slave address and address received interrupt, and slave receiver start detection for auto wake up from low power modes. The eUSKI-B module in I2C mode supports 2 different ways of implementing multiple slave addresses at the same time. It can do hardware support for up to 4 different slave addresses, each with its own interrupt flag and DMA trigger, or software support for up to 2 to the power 10 different slave addresses, all sharing one interrupt. The register's I2C own address 0, own address 1, own address 2, and own address 3 can contain 4 different slave addresses. Up to 4 address registers are compared against a received 7 or 10-bit address. Each slave address must be activated by setting the enable bit in the corresponding address register. Register own address 3 has the highest priority if the address received on the bus matches more than one slave address register. The priority decreases with the index number of the address register so that own address 0 in combination with the address mask has the lowest priority. When one of the slave registers matches the 7 or 10-bit address seen on the bus, the address is acknowledged. Following this, the corresponding receive or transmit flag that matches the received address is updated. The state change interrupt flags are independent of the address comparison result. They are updated according to the bus condition. Another interesting feature is the clock low timeout. This feature is useful for SM bus applications where a restriction has been placed on the duration for which the clock line can be held low. Using the built-in timer source allows the I2C module to perform the clock low timeout function without using up a system timer resource. The real-time clock module in the FR59X family provides clock counters with calendar mode, a flexible programmable alarm, and the ability to perform calibration. The RTC module is functional in LPM 3.5 when the core LDO is turned off, allowing for extremely low current consumption while maintaining the RTC count. Wake-up from this mode can be in the form of event triggers or alarms. On wake-up from LPM 3.5, the device undergoes a reset similar to a brownout reset, and the RTC registers such as the interrupts need to be re-enabled on startup. Comparator E is an analog voltage comparator that can support up to 16 independent channels. The Comparator Ii module supports precision slope analog to digital conversions, supply voltage supervision, and monitoring of external analog signals. In capacitive touch applications, the programmable voltage hysteresis generator in the comparator is very useful. Some of the other features of the comparator include inverting and non-inverting terminal input multiplexer, software selectable RC filter for the comparator output, outputs that are internally tied to timer A capture input for capacitive touch applications, ultra-low power comparator mode, and interrupt-driven measurement system for low-power operation support. This concludes our session on MSP430FR59X core architecture and peripherals. The next module will cover the usage of the FR5969 launchpad tool. Thank you for listening.